Okay, everybody, welcome back. We're doing more stoichiometry today, okay? Again, what is stoichiometry? It's how we use balanced equations, okay? You balance the equation, and then you can use that balanced equation to make predictions, very powerful quantitative predictions about what you're going to get, okay? That's stoichiometry. And remember what stoichiometry shows us. Relationship between the reactants and products in a reaction, and the coefficients that you balance the equation with, that's a ratio in moles, okay? And that ratio, those coefficients, give us a way to convert from one substance to another substance in the reaction, and that's how we're making our predictions, okay? And keep in mind your method for doing stoichiometry. You want to balance the equation and then make sure that you have moles, grams, or liters. Choose your pathway and then set up and do the problem. Okay. Now, some things you want to keep in mind here. Excuse me. The past 2 days, we've done mole to mole and gram to gram conversions. And those are good if you're dealing with solids and liquids, okay? But the reality is that in a chemical reaction, you may also be dealing with gases, and that, not gasoline, but rather matter in the gas phase, okay? So for those, we can use these 2 pathways, moles to liters or grams to liters, okay? And you could even reverse it and go from liters to either moles or grams, okay? Now, what we know to be true about gases, okay? 1 mole of any gas, and you can see it there at the bottom of that mole box, 1 mole of any gas in normal conditions is 22.4 liters in volume. It doesn't matter what the chemical is, what the compound is, but if you have 1 mole of particles, Avogadro's number worth of gas particles, okay, 1 mole of them is 22.4 liters, okay? So that allows us to easily and consistently convert from moles or grams into liters, okay? And that's what we're going to do here with 2 more examples, okay? So for the first problem, we have this equation again, water, or rather hydrogen and oxygen reacting to form water. So in this first problem, we have 6.2 moles of oxygen. How many liters of oxygen? Sorry, we're going to switch that up. Oh, and my apologies, everybody. We have 6.2 moles of hydrogen. How many liters of oxygen do we need to react with it? Okay, so first step, balance the equation. 2, 1, 2, okay? And again, if it's a 1, you don't have to put the 1. I will, just for clarity's sake, okay? Next step are our starting amount, 6.2 moles of hydrogen. It's in moles, so we're good to go, okay? Next step, choose your pathway. I'm given moles, and I want to know liters, okay? So the way we're going to set that up, moles of substance A, which is the hydrogen, we're going to put that over 1, factor label style. And then we're going to multiply that by a fraction where the coefficient of the oxygen is going to be over the coefficient of the hydrogen, because hydrogen is substance A, air quotes there. It's what we're converting from, and the oxygen is substance B. Okay, so these again are coefficients from the balanced equation. And then we're going to add 1 additional fraction where 1 mole is in the denominator and 22.4 liters is in the numerator. Because again, for gases, that's our conversion factor from moles to liters. Okay, so let's go ahead and set that up. 6.2 moles of hydrogen over 1, okay? And then the next fraction, moles of substance B, coefficient from the balanced equation, over moles of substance A, coefficient from the balanced equation, okay? So hydrogen goes in the denominator. It's because we want moles of hydrogen to cancel out. Its coefficient from the balanced equation is 2. So we put a 2 there, okay? Again, in this step, the numbers come from the balanced equation, the coefficients that balance the equation, okay? In the numerator, 1 mole of O2. And where did that come from? Right here, okay? 1 balances oxygen in this equation, okay? So moles of hydrogen cancel out. We're left with moles of oxygen. Next fraction, oxygen is a gas, okay? So on the bottom here, this is, mole to liter, that last fraction, 1 mole of oxygen goes on the bottom, and then the numerator, 22.4 liters of oxygen, okay? And again, that's just what we know about gases. 1 mole of any gas, including oxygen, has a volume of 22.4 liters, okay? So moles of oxygen cancel out, and we're now left with liters of oxygen as our units, okay? So at this point, your problem is set up. You want to calculate, okay? What I would do here on my calculator in parentheses, 6.2 times 22.4, that's everything in the numerators, and then divide that by the denominator, which is just 2, okay? 6.2 times 22.4 divided by 2, and the answer, 69.44. I'm going to round that to 2 significant figures because the original measurement has 2 sig figs, okay? So 69 liters of oxygen, okay? So to fully react with the hydrogen, we need 69 liters of oxygen, which, 22.4 liters is about the size of your average beach ball. So imagine about 3.5 beach balls, and that's the volume of oxygen we're dealing with, okay? So if you were doing this reaction, you would then know you would need that much oxygen, okay? All right, let's look at one more. So for this example, we're actually going to reverse the reaction. Imagine we have 250 grams of water. If we were to decompose the water through something called electrolysis, how many liters of oxygen would be produced? Electrolysis is when we take water and run a powerful electrical current through it, and that current, the energy is enough to split water into hydrogen and oxygen, okay? So an average glass of water here is about 250 milliliters, which is about 250 grams, okay? So if I were to take this water and completely split all of it into hydrogen and oxygen, how many liters of oxygen would I get, okay? So balance the equation, 2, 1, 2, okay? And then our pathway, grams to liters. I'm going to start with grams of substance A, the water, go from grams to moles by using the formula mass, much like we did with the gram-to-gram problems, and then coefficients from the balanced equation, water on the bottom, oxygen on the top, and then for the last fraction, again, because oxygen is a gas, 1 mole of oxygen on the bottom, 22.4 liters of oxygen in the numerator, okay? So let's set that up. 250 grams of water over 1, okay? Next fraction, 1 mole of water over water's formula mass. So again, from your periodic table, you would add 2 hydrogens and 1 oxygen, H2O, and that gives you the formula mass of water, which is 18.02 grams of water. So 1 mole of water is 18.02 grams. Next step, we're going to use coefficients from the balanced equation, okay? So water, because it's substance A, okay, air quotes there, sorry. Because it's substance A, we're going to put its coefficient on the bottom, 2 moles of H2O. And again, these are ratios in moles, as I've been saying. On the top, we want to know about oxygen. That's substance B. So 1 mole of oxygen. Okay. So grams of water cancel out, moles of water cancel out. We're left with moles of oxygen. Now, because oxygen is a gas in our pathway, we're going to use this final conversion factor. 1 mole of oxygen on the bottom, 22.4 liters of oxygen in the numerator on top. Okay? And there it is. Okay? Moles of oxygen cancel out. And our units, we're left with liters of oxygen. Okay? Again, for any gas, 1 mole of that gas in normal conditions is 22.4 liters. Okay? So again, if we were to take this cup of water and completely split all the water atom molecules in here into hydrogen and oxygen, how many liters of oxygen would be produced? Okay? Take a moment and pause and see if you can calculate. Okay, so when we do that, 250 times 22.4, that gets divided by the product of 18.02 times 2. Good way to do that on your calculator, I'm going to use parentheses again. Okay, 250 times 22.4 in parentheses, divided by, in parentheses, everything on the bottom, 18.02 times 2, close my parentheses, and there's the answer. Okay. Again, I'm going to round to 3 significant figures here. 155 liters of oxygen would be produced. Okay. So that's your answer. Again, if I were to split this water into its elements, they would be gases at room temperature, okay, not liquid, and I would get 155 liters of water from that process, okay, which, if we, in terms of beach balls, that would be about 7 beach balls filled with pure oxygen, okay, or 50-gallon drum size, kind of, pretty similar, okay? Okay, so stoichiometry, we can even extend to gases and to matter in the gas phase. All right, everybody, again, there'll be some practice problems here. Do your best, and let me know if you have any questions. All right, take care, stay safe. Wash your hands. All right, everybody, I'll see you later.